Okay, in lesson 3.2, we're going to be looking at finding the maximum and the minimum on an interval. So one of the terms that we need to know is the term extrema. On an interval, a function will have an absolute maximum and an absolute minimum. These are called the extrema, or the extreme values on the interval. So extrema is just another term for maximums and minimums. Now, the extrema could be at a local maximum or a local minimum. So I want you to imagine in this picture here, I've cut off the function at some x value a and some x value b, but the function actually would continue from here, right? So like maybe it goes down like this, or maybe it goes up and then down, and I don't know what it does. But all I'm interested in is this interval from a to b. So I've kind of erased these extra chunks here. I don't care about this outside portion. So when I look from A to B, what I'm asking for is what is the maximum value and what is the minimum value. So here they actually ended up being a local maximum on the entire function and a local minimum on the entire function. But on this interval, this is the absolute maximum and this is the absolute minimum. So hopefully you remember those terms, absolute and local, from advanced functions. If not, you can Google them. In the second version here, when we cut off our interval, so again, I've got my x value here at a and another x value at b. I've cut off that chunk of the function, so I'm ignoring the section down here and the section up here. When I look on this interval here, the minimum is still, here the minimum is this point here. It's actually the endpoint of the function instead of being this point here. This is a local minimum, but the absolute minimum is down here. And then again, the local maximum is here, but the absolute maximum is up here. So it can be on one of the endpoints. Or it could be a combination of the two. So in this last picture here, again, we've cut off the function at x is a and x is b. And our minimum this time is one of the endpoints of the interval. And the maximum this time is one of the local maximums in the middle. So there's kind of three cases that what can happen. When we try to find these maximums and minimums on an interval of values, we're going to go through this algorithm. So if the function has a derivative at every point from a to b, then what we're going to do is find the derivative. Then we're going to find the local maximums and minimums. So remember, to find these local maximum minimums, the tangent line at these guys is going to be 0, or sorry, the slope of the tangent line will be 0. So what I'm going to do is set the value of the derivative equal to 0, and then I'm going to solve for the x values. That's going to tell me what is this x number here and what is this x number here when I do that. The next thing I'm going to do is find the y values, or find the heights at all of the local maximums and minimums and at the endpoints of the intervals. So now I'm going to be figuring out what is this number across from this endpoint, what is this number across from the local minimum, and what is this number across from the endpoint. They just happen to be the same height on this example. Or over here, I'd be finding the height of this endpoint, the height of this endpoint over here, the height of this local maximum over here, and the height of this local minimum over here. And then once I've got those 4 y values, I'll just compare them to figure out which one is the largest and which one is the smallest. All right, so we're going to try this. We've got a cubic function here, so you might remember that it kind of does look like this here. I don't need to graph it here, though. All I'm going to do to find the absolute extrema on the given interval is take the derivative and set it equal to 0 to find those x values. Those are my first 2 steps. So taking the derivative, this one's a nice easy one. We'll bring the exponent down and multiply it with the existing coefficient. Subtract 1 from the exponent. Bring the exponent down, multiply it with the existing coefficient. Subtract 1 from the exponent. And the derivative of a constant is just 0. Now that I have the derivative, the next step in my algorithm tells me to set it equal to 0. This is where I'm finding horizontal tangents. And now to solve this one, I've got a quadratic, so I need to factor. There's a common factor here of negative 3x. You could also have taken out a positive 3x. You're going to come out with the same answer at the end of the day. And now what I've got here are 2 factors that I need to set equal to 0. So the first one here, we've got negative 3x could equal 0, or x minus 4 is equal to 0. And so that tells me that either x is equal to 0, or over here rearranging and solving, x is equal to positive 4. So now I've got 4 x values that I need to consider. These are local maximums or minimums. I'm not sure which ones. And this one here, I've got my endpoint on the left and my endpoint on the right. And I want to know how high is the function at each of these x values. So we're going to figure that out. So we're just going to take our original function and plug in all 4 of these x values. I'm going to start with the endpoints, but it doesn't matter really. This one comes out at a height of 86. And then the other endpoint. All right, the third one here, the f at 0, I didn't show much work because when I plug in 0, I get 0 plus 0 plus 5. And so I could do that in my head. So here I was, just for communication, I'm checking the y values in this section here. And now I'm on to the last step. I just have to compare all of these heights and figure out which one is the highest and which one is the lowest. So I can see here that my maximum is there, so it's going to happen when x is negative 3, and my minimum is 5, and that's going to happen when x is 0. So I just have to put that all into a sentence. Now this is of course true on this specific interval, right? So on the interval that was given here, and I'm going to state both. I'm going to state the minimum value, so of 5, at, and I'm going to say where did that happen. It happens at x equals 0. All right, so that's example 1. We're going to check out another version of the same question. We've just got a more complicated equation this time. But I'm going to start the same way. I'm going to take the derivative. This is capital I. When I take the derivative of this, I've got a quotient rule. I've got something with t's divided by something with t's. So I might be thinking off to the side about my quotient rule, f prime g minus fg prime all over g squared. And so these rules are coming back to us in this unit. So taking the derivative of the numerator, I get 2t plus 2. And then I'm going to multiply by the denominator. And then I'll subtract. This time I'm going to leave the numerator alone. And I'm going to multiply by the derivative of the denominator, which is just 1. And then I'm going to put that all over the denominator squared. All right, now what we need to figure out is where does this derivative equal 0? So I'm going to set it equal to 0. This is kind of like step 2. And I need to simplify this guy on the right here so that I can try and figure out when this equals 0. So I don't see any common factors in the numerator, so I am going to expand out these first 2 brackets here. So I get 2t times 2, that gives me 4t's, plus another 2 times t, so 4t plus 2t gives me 6t. And then I'm just going to distribute this negative through this bracket. Okay, now that I have 0 equals the fraction I can take that denominator and multiply it up to the other side of the equation to simplify things. But when I take this denominator and multiply it up, I'm going to get 0 times the bracket, which is just 0. And so I'm just left with 0 is equal to the numerator. You can collect like terms at that point if you want, but I'm just writing it out for emphasis. So most people are going to skip right to the step where they collect these like terms. All right, and now it's looking a little bit friendlier. We've got a quadratic equals 0. So to solve a quadratic, we set it equal to 0, and then we factor it and set each of the factors equal to 0. So here I'm looking for two numbers that multiply to negative 12 and add up to 4, and so the numbers are going to be positive 6 and negative 2. Remember, when it's a simple trinomial, there's a 1 in front, just because I've seen some people doing this. You don't have to use decomposition. You can just go straight to the t at the front of the bracket, and those two numbers that we found, positive 6 and negative 2, just pop into the brackets. All right, now these ones are nice and easy to solve. Remember, if I have something times something equals 0, either the first bracket has to equal 0, in which case the t value would be negative 6 to make that 0, or the second bracket equals 0. So the t value here would be 2. And so I've got my two t values, and I also have my two endpoints on my interval. Now notice though, in this one, my interval goes from 0 to 14, and my one t value is negative 6. Now this is not in the interval. So I'm going to write that. I recognize that it's not in the interval, and that tells me I don't need to consider it. So I want you to imagine a function. This one here is a little bit more complicated, but let's just imagine like a cubic for a second. What's happened here is I've cut this off, and I'm not including one of the minimum or the maximum points. It could be a totally different function, right? But this guy here is not in my interval, so I'm not going to think about him. I'm only going to consider this one and the possible endpoints. And again, this graph does not match this equation. All right, so now we've got our three t values. We only have to check three t values, and we need to find the heights. So we're going to check those y values. And when we do that, we're plugging those t values into the original equation. So again, I'm going to plug in my two endpoints. So I'll plug in I is equal to 0. And so I'm going to get 16 over 2. All right. And then I'm going to plug in I at 14. This one's a little bit more complicated. And I get 15. And then the last one we're going to plug in is I at 2. And when you're subbing in, you can do a little bit of simple arithmetic along the way here. We've got 2 squared, so that's just 4. And then we've got 2 times 2, so that's just 4. And then on the bottom, we also have 2 plus 2, which is also 4. Lots of different ways to get 4 here. And that comes out to 6 then. And so we've got our all of our y values. Now we're just looking at them, which one's the biggest and which one's the smallest. And then we're going to write that into our summary sentence, and we're going to include those x values that we plugged in. It doesn't matter which one you do first, maximum or minimum. And so in that summary sentence, you're communicating to me that you know which number here is the maximum, right? Like you're not getting the x and the y values mixed up. You know that the 15 represents the maximum value and the 14 is just where it occurs. All right, in example 2, we're going to look at a word problem. This time we're looking at the position of a particle moving horizontally is given by s at t, and s at t is a cubic function. S is in meters, and the time t is in seconds. We're going to find two different things here. First, we're going to find the maximum and minimum distances. So whatever I'm maximizing or minimizing, that's the thing I want to take the derivative of. Now, s at t is a position function, which is similar to a distance. So I want to take the derivative of the given function. So just bringing the 3 down, multiplying it with the existing coefficient, subtracting 1 from the exponent, bringing this guy down, we get 2t, and then plus 21. Now we're going to set this one equal to 0, part of our algorithm, right? That means I'm just looking for horizontal tangents. And now we're going to try to factor this. Now, one thing that you can do to simplify this a little bit before we try to factor is I can divide a -1 out of all of the terms. So when I divide 0 by -1, I get 0. And then when I divide these guys by -1, it's just going to flip the sign. It just makes it slightly simpler when we have a positive lead coefficient. Now, what I'm going to do is decompose this guy to factor him, or if you're comfortable, there are other methods here that you can look at. I know that the two lead terms are going to be 3t and t, and then I just have to kind of play around with those numbers, like the box method or other things like that. Choose your method of choice. You should come up with +7 with the 3t and -3 with the regular t. So most of you are going to show me some more steps there. All right, now that I've got the two brackets being multiplied, I can set each factor equal to 0. So I can say that either the first bracket equals 0, and in that case, I would bring the 7 over. I'll just write that out. So either the first bracket equals 0, in which case here the 7 would come over, and then I would divide out the 3, or the second bracket equals 0. That one's a little bit simpler to solve in our heads. Now again, I'm going to check these values on my interval. My interval goes from 0 to 5, so this negative value is not in my interval. So I'm going to write that down to show that I thought about it, I didn't just forget about it. And again, I have 3 values that I need to check, 0, 5, and 3. When I plug in s as 0, again, I'm using the original function here. I'm going to just get 0. And for s at 5, I get 5. And then we'll check the t value that we found over here. This is a local maximum. We need to figure out if it's also an absolute. And that one comes out to 45. So looking for our maximum and minimum distances, we've got the biggest number is 45 at 3 seconds, and the smallest is 0 at 0 seconds. So when I write a summary sentence about a word problem, I'm always going to change the values into part of the story. So instead of using this interval notation, I'm going to say between 0 and 5 seconds. And instead of talking about the maximum value in this story, the maximum and minimum values are distances, so the maximum distance. Oh, getting ahead of myself. Okay, so that's part A. Now in part B, they ask me about finding the maximum and minimum velocities. So this time I need to find the derivative of the velocity function. So I'm always taking whatever I'm trying to maximize or minimize, that's what I'm taking the derivative of. So I need a velocity function. So I'm going to remember from 3.1 that the velocity function is equal to the derivative of the position function. And so here my derivative of my position function was negative 3t squared plus 2t plus 21. So this is my velocity function. This is the one that I want to take the derivative of in order to maximize or minimize. So taking the derivative, I get negative 6t plus 2. And now to find the horizontal tangents, those local maximum and minimums, I want to set the derivative value equal to 0. And then I'm going to rearrange and solve. So I'm going to get this one here, I'm rearranging and solving because it's already linear, right? There's no quadratic here to factor. And so I get 1/3 for my t value. Now my interval here goes from 0 to 5, so 1/3 is in my interval. I just need to check those 3 y values. This time when I'm checking, I'm plugging them into the original function, and remember the original function this time is the velocity function. So I'm checking them in this equation. This time when I plug t equals 0 in, I'm going to be left with the 21. And my other endpoint was 5. Just squaring the 5, I get 25. And altogether that comes out at negative 44. And this one here comes out to 21 and 1/3 as a mixed number. I'm leaving it as a mixed number for this question because we're talking about velocities, so having an improper fraction isn't going to make a whole lot of sense here. And then again, I'm looking for my maximum and my minimum velocities. So velocity does include direction. So this is my minimum, even though it's actually the fastest speed, it's the minimum velocity. And then my my biggest will be then 21 and 1/3, which happens at 1/3. And we'll put that into a sentence. And so, oops, 44, not 41. I can interpret negative 44 meters to this, per second is the same as 44 meters per second to the left, right? When we're given a position function, by default, the positive is moving to the right. And so here, if I have a negative, it means that the velocity is heading to the left. And this one here occurs at 5 seconds. And all right. And that's it for today's lesson. Enjoy the homework.